Hello, everyone. I'm really sorry I couldn't make it in person, but my name is Yotam, and today I'll be talking about sharpness-aware flow matching inference. So we all know that generative models have actually been working really well for scientific discovery, but we're going to look at how we can leverage geometry and kind of move away from the brute force computation that's used in generative modeling towards a more model-aware inference approach. Yep, so as we know, generative modeling has been deployed in many scientific applications, ranging from climate modeling to protein folding, all the way to drug discovery and cell dynamics. One example in which this is used is doing super resolution for climate modeling, which has been very promising. But there is a bottleneck. While these models are very powerful, their inference cost has been quite restrictive. In scientific context, since we need to do many inference stages, we aren't just generating a single image. We need to generate thousands of samples for statistical significance, and the current methods are just too slow for these live applications. Our work specifically focuses on flow matching. Um, and as you can see from these images, we're able to generate quite high quality data. However, the generation of this data is actually quite expensive. Unlike one-shot models, flow matching requires us to solve an ordinary differential equation. This means that we have to run a forward pass on a very large neural network many times, maybe dozens or hundreds of times to generate a single sample. So this can be very expensive, and without the right tools, it might not even be worth doing. Okay. To understand why flow matching is expensive, let's look at the underlying mechanism by transforming a simple distribution, such as Gaussian noise, over to our target data distribution. So in standard flow matching, we're usually given a base distribution which is known and easy to sample from, such as the 1D Gaussian. And then we have an unknown target distribution, which could be the image manifold. Usually, we have a fixed number of finite samples of our target distribution. And flow matching defines this ODE called the flow ODE, in which this F, a neural network, is learned based on our samples. And then this ordinary differential equation is eventually solved to generate new images. So first, the training. The way that flow matching training works is first we try to define the simplest path between image and noise. So for us here, x0 is going to be considered our noise, and x1 is our image. So at any time t between 0 and 1, we have some linear combination between our noise and our image. So if we plug 0 into this equation, we see that we have 1 times x0, so pure noise, plus 0 times the image, so just pure noise. And at time 1, we have just the image because we have 0 times our noise, and x1, which is our image, is 1. So xt kind of defines this mixture between noise and image, where we take a noise sample and we take an image, and then we mix it together to get some sort of mix between both. Now, after we've defined this path, what we do is we take the derivative of x of t with respect to t. So coming from a math background, this really excites me because I get to do some simple calculus in front of you. But yeah, so if we take the derivative of 1 minus t with respect to t, we get -1. And when we take the derivative of t with respect to t, we just get the number 1. So when we take the derivative of t along this path, we just get -x0 plus x1. So our neural network, which is trying to approximate dx dt, we know that all that it should evaluate to is x1 minus x0. So the math underlying flow matching is actually not very complex. All you need to know is that we minimize the mean squared error objective between the neural network, which is f, and then the image minus the noise. So what we do when we're training this model is we take thousands of images, if not millions of images, and millions of different time points. We pick a time point, which tells us how much we should noise our image. And we put in our noised image, so x of t and the current time into the neural network. And we want the output to be the image minus the noise. So we repeat this process millions of times, and we're able to train our neural network. So once we have a trained neural network, here we're going to look at a very simple example where our trained neural network, what it does is it takes points from a two-dimensional Gaussian and it maps them to the checkerboard. So this graphic is showing you us taking 5,000 new noise samples and then kind of moving through this flow ODE. So doing a simple ordinary differential equation solve where we move between noise and the image. So our trained vector field F or flow field actually tells us how we should move forward in time. So the first image is at time 0, then the second one is at time 0.25, time 0.5, 0.75, and then time 1. And what we kind of see is if we look at the distribution of points as we move in time, they converge to our expected distribution. And the way that the points move from left to right is by doing a discrete integration or forward Euler in the simplest case, where we take our time domain, we split it evenly, and then we evaluate our neural network iteratively. So we take these points and we plug them into the neural network to get these points, and then we plug them into the neural network to get these points, and so on until we converge to our final time step. Now, that's a really expensive iterative process, and it does not leverage any information about the model. So we propose this new paradigm where first we run an expensive offline state to analyze the geometry of the learned vector field. And then once we learn the underlying geometry, we're able to more intelligently place our time points and either accelerate our inference or get more value out of our inference steps. So I ran the sharpness profiler on Stable Diffusion 3, which is a state-of-the-art image generation model. And what we were able to observe across many different prompts, across many different seeds and trials, is that we see high sharpness or challenge difficulty integrating at the start of the process when we're close to a noise sample, and low sharpness and easy integration when we're close to an image. So this kind of allows us to bias how we're going to do our solve step. So what we do with this average sharpness across prompts and times is we take it and then we quantize it to generate a new time step schedule based on a fixed time step budget. And kind of what we were able to observe is that our time step budget allocates a lot more times earlier in the process than either doing the uniform time step, which is in blue, or the shifted uniform time step, which is a heuristic-based time step that Stable Diffusion 3 uses. So we use the green line when doing integration. And what we learn is that we are actually able to outperform both the uniform, which is the default integration scheme where we take the time 0 to 1 and we chop it up evenly, and the shifted uniform, which is a heuristic-based method. So our approach is data-driven, and we outperform existing methods both when looking at the images themselves. Over here across the first row, we see an image of a person with a glass sculpture, and on the uniform stage, we see that When using uniform time steps, the images don't come out very good. When using the shifted uniform, the images look reasonable, but we see that the hand might be a little bit messed up. Whereas if we use the sharpness aware time points, so the cost of generating all these images is the same, but the quality of the rightmost images is the highest, which leverages information about the neural network. Additionally, when looking at reconstruction error, we are able to see that as we increase the number of function evaluations or our compute budget, we continue to outperform the existing methods. So in conclusion, by leveraging the geometry of the underlying space, we're able to, under the same fixed compute budget, generate much higher quality images. We were able to reduce the error by up to 35% for the same cost images. And this unlocks the potential to improve inference for many scientific applications, which we'd like to explore in the future. Thank you so much. Bye.